Hey everyone, Houston Math Prep here to introduce the idea of the matrix equation AX equals B. We're going to start with the idea of a linear combination. Here we've written a linear combination of vectors. You can see we've called our vectors A in each term. So we have vectors A1, A2, A3, etc. Of course, in order to add these vectors together, we'll keep in mind they all have to have the same number of entries in them. Our x values here, x1, x2, and so on, are just the scalar multiples of each vector that it's partnered with in our linear combination. Now, if we took all of these vectors and multiplied them by their scalars and then added them up, all of this would add up to another vector. And we're going to call this vector b for now. Of course, vector b would have to have the same number of entries as the other vectors for the addition to work. And we'll call the number of entries that all these vectors have m. So each vector has m entries, and you can tell by our linear combination here that the number of vectors we have is n. So n is the number of vectors on the left side, m is the amount of entries in each of these vectors, including vector b here. We're going to start showing you how we can think of this equation in a matrix form. So first, imagine that we take all of the vectors on the left side of the equation here, all of my A vectors, A1, A2, etc., and we make a matrix out of them, keeping them in order, where each vector is a column of this matrix. So I've got my n vectors are now the columns for this matrix here. And we'll call this matrix capital A, and my lowercase a vectors are now just the columns of my capital A matrix. Each vector has m entries, and there are n vectors, so our matrix will have m rows, n columns, making its size m by n. And now let's also take all the scalars, all of our x values, and put them together in order into a column vector. We'll go ahead and give our vector with all the x value entries in it a name, and we'll call it vector x. That'll be easy to remember. Now, how many scalars are there that went into this vector x? There are n of these scalars, so there will be n entries in this x vector, and so its size will be n by 1. Now, for combinations of vectors in matrix A to be able to add together to give us vector b, the a vectors and the b vector will need to have the same number of entries. We know that matrix A has m rows, so vector b will also need to have the same number of entries. So b will have m entries as well. Its size will be m by 1 as a matrix. We'll show you an easier way to see this in just a second, but this is how we build our matrix equation. Matrix A times the vector x is equal to vector b. Let's look at some examples that'll make it easier to see how equations that include combinations of vectors can be written in this ax equals b form. So for this first one here, if we have x1 times the vector 2, 4, plus x2 times the vector 6, 8 equal to 1, 3, we can see, of course, the right side is staying the same. What we're actually doing is taking each vector in our linear combination here. Our right side really isn't changing. What is changing is that we're taking this linear combination of these vectors, writing the vectors together in order in a matrix, and combining our scalar multiples here into a vector together. So this one here where we have 3 vectors and 3 scalar multiples, we take each of those vectors, create a matrix that has 3 columns in it. We take our x1, x2, x3, put them all together in a vector, and we have our matrix form. For this last one here, we want to make sure everybody understands that we don't have to have the same number of vectors as we have entries in each vector. So here we had 2 vectors each with 2 entries. Here we had 3 vectors each with 3 entries. Here we only have 2 vectors each with 3 entries. So again, we take these column vectors here, we make a matrix with those columns. This is our matrix A times our vector with our x scalar components in it, equal to our vector b still on the right side. So really, in our linear algebra video series so far, we have three different views of how to represent a linear system of equations. The first one, of course, just being our system in equation form. We've also talked about how to rewrite this system as a linear combination of vectors. And now we have another way of thinking about this, combining each of these vectors into a matrix, what we typically think of as the coefficient matrix, times our variable vector x equal to our vector on the other side, which we're calling b. This way of seeing the matrix equation is mostly based on thinking of things in columns so far. Once we've covered matrix multiplication in our linear algebra series, we'll look at this matrix equation in more of a row-focused way. Let's take a look at an example of a system in ax equals b form, where it's asking us to solve the following system for, notice the vector x here, which means we're solving for all of the scalar multiples as we used to think of it. So if we think of our augmented matrix for this system, then our augmented matrix is going to look like 1, -3, 5 for the first column, 2, -4, 6 for the next column, and our b column over here joining as our final column, -1, -1, 3. So what we have here is a column of information pertaining to x1, a column of information pertaining to x2 here. This is our b. So if I go about row reducing this, thinking about I have a 1 here in the top left corner, that's nice, so I can begin creating zeros below that 1, doing row reduction. So if we add 3 copies of this 1 to this -3, that will make it a 0. So we're going to change row 2. We're going to make it row 2 plus 3 copies of row 1. And if we write that down for the second row, -3 plus 3 of those 1s would give us a 0. 3 of these 2s would make 6, so -4 plus 6 would give us 2. 3 of these -1s would be -3, and if we add that to the -1, that would be -4. We'll go ahead and copy everything else down. And then what we'll need to do is think about getting a 0 where this 5 is. So what we'll do next, off to the side here, we will go ahead and change row 3. We're going to change it by subtracting 5 copies of this 1 from it. So it'll be row 3 minus 5 copies of row 1. And once we do that, we'll have 5 copies of row 1 gives us 5. 5 minus 5 would be 0. 5 copies of this 2 would be 10. 6 minus 10 would be -4. 5 copies of this -1 would be -5. Be careful here. 3 minus -5 would actually be like +5, so that's an 8 there. We'll go ahead and copy down the other stuff that we have. I'm going to go ahead and keep working sideways here. So I'm going to create a 1 here in this second row where my lead entry is. So I'm just going to take row 2 and I'm going to divide it by 2. So row 1 will stay the same, 1, 2, -1. Row 2 becomes 0, 1, -2. Here we have 0, -4, 8. You might already sort of see what's happening. And with row 3 here, if I want to make a 0 below my lead entry, what I would need to do then, if I go up here, we would need to change row 3 by taking itself, and we'll add 4 copies of row 2 to it. And so our final row then would become, we'd have a 0 there. 4 of these 1s would make 4. -4 plus 4 would be 0. And then 4 of these -2s would make -8. So 8 plus -8 would be 0. We get all zeros there. 0, 1, -2, and 1, 2, -1. All right, so let's go ahead and take the final step here. We'll go ahead and get it in reduced echelon form. I'll go ahead and reduce this 2 above my lead entry of 1. And so what we'll need to do finally will be to take row 1 that we're going to change, And we will go ahead and subtract 2 copies of this 1 to make a 0 there. So it will be row 1 minus 2 copies of row 2. So our row 1 ends up as a 1. 2 copies of this would be 2, so 2 minus 2 is 0. 2 copies of this would be -4, so -1 minus -4 would be like +4, so that becomes a 3 there. I'll copy down what we have otherwise, and you might start to see what our solution is. So remember, this column here tells us about x1, this column here tells us about x2. Of course, these are our b values. So our first row here tells us that x1 is equal to 3. Our next row tells us that x2 is equal to -2. And this here really just says that 0 equals 0. That doesn't change the system from being consistent. This is a true statement here. It doesn't give us any additional information other than it verifies we don't get any false information. So this is a consistent system, and it looks like we get 3 for x1 and -2 for x2. And if we want to check and make sure we got a true statement there, that these answers are valid, then we could take 3 times our first column, 1, -3, 5. And since x2 is -2, so -2 times column 2, which is 2, -4, 6, is equal to our b column over here, -1, -1, 3. And if you do the math here, you'll see that it actually does work out. If we just look at the first row, for example, 3 times 1 would be 3. -2 times 2 would be -4. So 3 minus 4 gives us this top entry, -1. And you can go down the list here and see that each of the entries in the respective places works out. Here at the bottom, 3 times 5 is 15. -12 here does give us 3. And so it looks like a good solution here that x1 is equal to 3. And x2 is equal to -2, or if we want to write this just as a vector, we could say our x vector that works is simply the vector 3, -2. Now, real quick, I want to point out the extra thing we had going on with the third row, which was nothing that messed up our system here from being consistent. I want you to imagine maybe if we had a different entry here than 3. Let's say we had something in its place like 6 instead. If we worked this out with -1, -1, 6 to begin with, we do all the row reduction, what you would have ended up with here is some sort of a row at the bottom that would have looked like 0, 0, 3. You can work that out if you want to, just by changing this 3 to a 6, and you'll see that this third row would become something like 0, 0, 3. And think about what that says. That says no x1s plus no x2s equals 3. In other words, this row we would get would be a statement of 0 is equal to 3. Now that would make our system here inconsistent. That would be no good. And even though we're getting that x1 is 3 and x2 is -2, because we get an inconsistent system here, if you go back and try and check this by using 3 and -2 for your x values, you see that you wouldn't actually get the vector -1, -1, 6 if we put a 6 in here when you go to check it. Let's take a look at another question. We're being asked, do the following vectors span R3? Do they span 3-dimensional space? And remember that span of a group of vectors is simply what are all the possibilities we can get from all of the different linear combinations of those vectors. Okay, so with one vector before, we talked about it in the previous video, it was a line. 2 vectors, it's a plane. Is it possible that these 3 vectors span 3-dimensional space? Can we get anywhere in 3-dimensional space using a combination of these 3 paths? And so what we're really asking is there a linear combination of these vectors so that no matter what we use for vector B, it will always work out? So for any vector on the right side, will we have an answer? And if we think about the matrix form of this, our AX equals B, that's saying let's have a matrix where the columns of that matrix are just our vectors times our x vector, right? Times our vector with x1, x2, and x3 values in it. We want that to have a solution no matter what we put in our b vector, b1, b2, b3. If it doesn't matter what we put in there, we can get to any point in three-dimensional space, right? So now, when will this be guaranteed to have a solution no matter what we have for b, right? We don't want any weird situations at the bottom where sometimes it could be 0 equals 0, but it could be 0 equals 5, and so one of them would be lots of solutions and one would be no solution. We want it to not matter what we put in the b column. And the way that happens is if this matrix here, if we call this matrix A, this matrix would need to have a pivot in every row. If it had a pivot in every row, then think about each row is going to give us a solution. We'll get a solution for x1, for x2, for x3, no matter what we put over here. So we don't need to try and make up a bunch of b vectors and then see what happens. That would be a lot of work. What we just need to do is row reduce a matrix that we create out of these vectors, v1, v2, v3, and see if we end up with a pivot in every row. So let's go ahead and make our matrix A out of these vectors. So it'll be 2, 1, 0, 1, 3, 2, and 9, 2, 1. Okay, we already have a 0 in the bottom spot here, which is nice. I'm going to go ahead and swap rows 1 and 2. So I'm going to go ahead and say row 1 and row 2 swap, so that I get a 1 in the top spot. That might be easier to reduce with. So we'll put the row 1, 3, 2 up there. We'll have the 2, 1, 9 below it. We'll have the 0, 2, 1 at the bottom still. Now I just need to reduce this 2 with my 1. We'll go ahead and do that down here. And so we will take row 2, will be the one we change, and we're going to subtract 2 copies of this 1 to give us a 0 there. So it'll be row 2 minus 2 copies of row 1. And so our row 2 here, 2 copies of this 1 would be 2. 2 minus 2 is 0. 2 copies of our 3 here would make a 6, so 1 minus 6 would give us -5. 2 copies of our row 2 here would make 4, so 9 minus 4 would give us 5. We'll keep our other rows the same for now. So now you can see we have a pivot here in our first row for sure. Our next row here, let's go ahead and reduce this -5 to a 1. So over here, we'll go ahead and take row 2, and we'll just divide it by -5. And doing that will give us 0, 1, -1. Keeping again our other rows for now the same. And we just need to make sure that we have a pivot in every row. So we'll keep going here. We need a 0 below this 1. So our next step, we'll go ahead and change row 3. And we'll need to subtract 2 copies of this 1 to get a 0 there. So we'll take row 3 minus 2 copies of row 2. And then, of course, adding copies of 0 to 0 doesn't change anything. 2 copies of this 1 is 2. 2 minus 2 is a 0 there. 2 copies of this -1 is -2, minus be like +2. So we have, again, our 1, 3, 2. We have our 0, 1, -1. And I think we can see just looking right here, we do have a pivot in every row. We could continue to sort of do the backward phase of the reduction and get 0s above this 1 and get a 0 above this 1 as well. But we do have a pivot in every row. We can see we're going to have a pivot here, and here, and here. And so it turns out no matter what vector b has in it, we will always be able to get a linear combination of these vectors that points to the same place that vector b points to. So do the following vectors span R3? Well, because we have a pivot in every row here, the answer is yes. This also tells us something. I think if we need a pivot in every row, imagine that we only had 2 of these vectors. We didn't have v3, for example. So if we made our matrix and reduced it here, we would have only had 2 columns, right? So we would have had 2 columns and 3 rows just using v1 and v2. We wouldn't have been able to get a pivot in every row, okay? So we could not span 3-dimensional space with only 2 of these vectors, right? We would definitely need at least a 3rd vector. We can't do it with less than 3 vectors in this case. Let's work through one more final example. Do the vectors here span 3-dimensional space? So we've got 3 different vectors here. If we go ahead and make our matrix A with these vectors v1, v2, v3 as the columns of A, then we will start with 2, 0, negative 2 is our first column, 0, 1, 1 is our second column, 1, 1, 0 is our third column. And no matter what vector we have for B, we want it to work. So remember, we just need a pivot in each of the rows in this matrix here. What I typically do, if it makes sense in my row reduction, is I try to get a 1 in this top spot. You'll notice that to get a 1 in this top spot, we would need to divide by 2, which would give me a half over here. Fractions aren't bad, but what I might notice is that simply adding this 2 to this negative 2 is going to give me a 0 where I want it. So let's not reduce row 1 for now. Okay, let's go ahead and change row 3. And what we're going to do is we're just going to add row 1 to it to give us a 0 there. That'll be nice. So it'll be row 3 plus row 1. So if we do that, the negative 2 plus 2 gives me a 0. The 1 plus the 0 gives me a 1 still. And the 0 plus the 1 up there gives me a 1. And we'll write everything in that we had besides that. So 2, 0, 1, 0, 1, 1. Now we can go ahead and make this top entry a 1 if we want. We don't really need to see what's going on, I think, down here, but we could. So let's just say, for instance, we take row 1 and we divide it by 2. So that would give us 1, 0, a half, and then we'd have 0, 1, 1, 0, 1, 1, which is the important part, right? Got a pivot here. It looks like we can make a pivot here. So now we would need to reduce below the pivot. We would need to make this a 0 below this pivot. So I'm going to go ahead and do this down here because it's going to be my last step. So I will take row 3. And the way we're going to change that is just to simply subtract row 2 from it. Now, if we do that, 0 minus 0 is 0. 1 minus 1 is 0. And 1 minus 1 is 0. So in trying to reduce just the one entry, you can see we actually reduced the entire row to all zeros, which is okay if we're looking for a consistent system. But what we're looking for here is, do the following vectors span R3? And remember, to do that, we said we need a pivot in each row of our matrix A that we made from our vectors here. Now, if we look in here, this is a pivot here, and this is a pivot here, but we don't have a pivot in the final row. Remember, a pivot needs to be a non-zero entry, certainly, and all zeros means we don't have that. If you think about extending this matrix and including that B column on the end, whether or not you had a 0 down here when you did your row reduction or some other number would determine if this last row is true or false, right? In other words, the system being consistent or inconsistent. So it would depend on what we put in the vector B. And so this is not going to span R3. It does depend on the vector that we choose for B. We will be able to span some of R3, certainly with these 3 vectors, but not all of R3.